All right. Now, we are moving on to an application of matrices, right? So earlier, or actually just like if you're doing this in a binge, right? We have been discussing, right? The different terms and definitions that you need to understand so that you can understand linear algebra. And so now we are going to the name linear algebra itself. We are just doing algebra. Mind you, we're doing lots and lots of algebra, but still, we are doing it nonetheless. And so now you might say to yourself, all right, cool, matrices, wow, very cool formulas, properties, whatever. Ano naman? Right? Where are we going to use these things? And so now I will present to you two, right? Two questions, right? Two questions wherein these are basically simultaneous equations, right? And I will solve it in two different ways, right? Of course, if you're going to solve this manually, pwede naman. Wala namang problema doon, right? We have here equation 1 and we have equation 2 and ikaw na bahala dumiskarte. If we're not asking, or rather, if I'm not asking you to do this based on linear algebra rules, what you will do is, well, what you might do is, say, for example, equation 2, you might now move your 5x to the other side. You will now have y is equal to 9 minus 5x. And you might substitute to equation 1. We will now have 2x minus 3 times 9 minus 5x is equal to negative 10. If we're going to expand, we will have negative 27. This is plus 15x. We will have negative 10 still. And then we will have in here 2x plus 15x, that is 17x. And if you're going to put the negative 27 to the other side, that is negative 10 plus 27. Your 17x equals 17. And then your x is equal to 1. Now that you know that, you can put it back to substitute it to equation 2. Substitute to equation 2, wherein your y is now equal to 9 minus 5 times 1. Now your y is equal to 4. And so this is what you'll expect, right? The answer is going to be. However, what if I told you that there may be a possible easier way out? Of course, the easier way out is to just use your calculator. But now, what if instead of doing this the manual way, I will call this the quote unquote the manual way, and instead we do something a little bit more matrixy. I will now introduce to you solving simultaneous equations based on matrices. Right? If you notice, there are both x's and y's in this case. And so now I will invite you to think about this in a matrixy way. What do we mean a matrixy way? Let's just copy and paste this whole thing. Copy. Then we'll paste it here. Okay, how are we supposed to solve this in a matrixy fashion? Now, let's think about this first, right? These two left-hand sides of these two equations. Notice that they can be written down like this. If you just look at all of their coefficients and keep them there, 2, negative 3, 5, and then 1, and then you have them with this matrix right here, x and y, notice that they will give you, right? This is a 2 by 1 matrix, 2 columns, 2 by 2 matrix pala ito. 2 columns, 2 matrices, 2 columns, 2 rows, 2 columns, right? And now we will have here a column matrix or a column vector, 2 rows and 1 column. So we can now cancel this. We will now have our new size, which is a 2 by 1 matrix, or in other words, another column. Another column vector. Excuse me, code. Okay. Ayan. Sige, you can be there if you want. Right? Notice that this is going to give us, right, a 2 by 1 matrix, aka, right, a column matrix or a column vector. So, right, for this case, right, our first column or only column is going to be first row only column. So this is 2x and then minus 3y. I see. And then for our second row only column, that will be 5x plus 1y, or just 5x plus y. So it turns out that if you're going to, kumbaga, right? How should we say this? If you're going to decompose this thing, if you're going to express this another way, it can be the product of these two matrices. Let's call this matrix right here matrix A, and let's call this matrix here matrix X. I will denote it with a small letter X, but this is still blackboard bold for us to understand that, hey, wait a second, that is a variable. Okay, and now what about this 10 and then this 9? Well, we can represent that as well with just another column matrix 10 and 9. Basically, what we're seeing in here is that for the first case, they are equal. For the second case, they are also equal because of this thing right here. So in other words, this thing can be written down as 2, negative 3, 5, 1 times xy is equal to 10 and then, negative 10 and 9. Negative 10 and 9. Now, everything here can be written down as matrix A times matrix X is equal to, let's just write this down as matrix B. B with a small letter so that we understand that it's not a variable, but also it's a column vector. Right? Column vector in this case usually, apparently, is written down with small letters. And so now, what? Ano naman? Right? What is up with AX equals B? Well, if I were to ask you, what is 5x equals 3? In this case, what would be your value of x? You would say, oh, duh, it's just 3 over 5. What's so difficult about that? Well, I will ask you now, what is so difficult about this? Right? For us to find our value of x, or basically our values of x and y, which is the value of this column vector x, we're just going to have to divide b with a. And of course, that sounds stupid because, again, matrix division is not defined. However, we can define it here. Or rather, we can still do it here if we just do this. We multiply the inverse of A. In this case, what we will create is inverse of A times X is equal to inverse of A times B. Okay, and notice that what I'm doing here is that I'm sticking this in at the first part, right? If I'm sticking this in here, I'm sticking this in here, right? Kumbaga, right? They are going to be at the first. And notice what happens when I do this operation. What is now this thing? Oh, that's just the identity matrix. Okay, so I times your x is equal to A inverse times your B. What is what is I times your x? Well, if we're gonna have to do this 1, 0, 0, 1, and then you multiply this by x and by y, this is just literally 1, but in the matrix world. So, of course, what you're going to expect is just x itself. And now if you notice, well, isn't this just our answer? If we can somehow manage to find, right? If we can somehow manage to find the inverse of A and then multiply that with B, isn't that our answer? The answer is yes, that is going to be your answer. And so honestly, we can already start by doing this, right? Let's just try and find our value of A, right? Our inverse of A. So first, that requires us to create, or rather to find the determinant of A, which in this case is 2 times 1 is 2, right? 5 times 3 is 15. So negative 15 pala rather. Oh, sorry, negative, and then there's a negative in here. So plus 15. We're going to have that 17 again. Okay, all right, whatever. Okay, so the determinant for this thing is 17. Let's try and find the adjoint now. And if you remember from last video, there is a pattern. What is the pattern in here? The pattern is, the pattern is you're just going to switch the values of your main diagonal 1 and 2. And then you're going to have to apply negative signs to either or to both of the other elements. So in this case, this will be 3. This is negative 5. And so the inverse of A will now be, you divide everything by 17, we will have 3, negative 5, and 2. We will now have basically this. And so our value for the matrix of X is just going to be 1 over 17. I don't want to apply that right now, right? So what we will do for now is just have this 1, 3, negative 5, and then 2. Our B in this case is going to be your negative 10 and then 9. And again, because here we have 2 rows, 2 columns, and in this case we have 2 rows and then 1 column, this gets cancelled. This is now your new size, row and column. This will still be a vector, a column vector or a column matrix. And so now, right, first row only column, first row only column, right? We will have what is this? Negative 10, right? Negative 10 plus 27, or negative 10 plus 27 is 17. Very interesting. And also, do you remember the negative 10 and the 27? Interesting, right? Okay. Anyway, right? So that's how you know that things are working their magic, right? And then we have here second row only column, second row only column. 5 times 10 is 50, right? And then your 9 plus 2 is 18. 9 times 2 is 18. So 50 plus 18 is 68. Wouldn't you know it? 68 is 17 times 4, which means now 17 over 17 and then 68 over 17 gives us a value of 1, 4, which is, right, our value of the matrix X, which is our X and our Y. Look at this, right? X equals 1 and then Y equals 4. This thing is Kramer's rule. If ever you have heard of that in fun math, I don't know, like 10 million years ago, right? This is Kramer's rule, right? This is Kramer's rule. And the only thing about Kramer's rule is that, as you can see, the requirement is you have to create the inverse. And, right, I'm already preparing myself because this is now a 3 by 3 example. You're going to have to create the inverse of a 3 by 3 matrix, which again, I understand you can very easily do this in a calculator. There are calculators in the internet that can, I don't know, calculate the inverse of 4 by 4 matrices for all I care, right? MATLAB can do it, right? That means that you can probably do it, but I'm asking here for the process, okay? And actually, there is another bit that we can do. How are we going to do this? Well, right, I'll just stick it here, right? We will be doing what is called Gauss-Jordan elimination. Gauss-Jordan elimination, right? This is for those of you, which is everyone, this is for those of you who do not want to create, this is for those of you who do not want to create the inverse of a matrix, right? In this case, very understandable that we want to just create the matrix and then have it be solved from there. I understand that, right? The allure, right? The advantage of making this of this linear algebra kind of constraint, or this kind of version of it, is it's organized, right? You can very clearly see, oh, this is the matrix, okay, that we are creating. And so now with Gauss-Jordan elimination, good news, you do not have to create the inverse. Bad news, you're gonna have to do some algebra. So pick your poison, right? Either you do the normal algebra version, or you do Kramer's rule, which requires you to create an inverse, which I mean is easy enough for a 2 by 2 matrix. But what about 3 by 3 matrix? A 4 by 4 matrix? What will happen then? The Gauss-Jordan elimination will now require you to just do a bunch of algebra for you to create basically a final result that is easy to read. What do you mean is easy to read? Our two goals, right? All right. Your goals are either number one, the row echelon form, or echelon. I don't know, right? Row echelon form, or the other one, which is the reduced row echelon form, R, E, F. And so now, how are we going to get there? We have to create what is called the augmented matrix. Augmented is in changed, right? How do you change this? 2, -3, 5, and 1. Basically, you're going to make this X and Y disappear, right? You're going to create this extra long matrix, which is just the combination of your A and your B matrices. Okay, so this is just your A and your B matrix. What is the row echelon form? Or basically, what is the stopping point? When do you know that you have gotten to an answer that is legible, that is intelligible? Your goal for the row echelon form, if you want to make it that way, is for you to create basically an upper triangular matrix. So you're like, what is an upper triangular matrix? Create a triangle within a square matrix, right? Say, for example, you have here 3 by 3 matrix, right? These are the values of your matrix. Create a triangle. Okay, that is your upper triangular matrix, because if you tilt your head like this is the upper side, right? This is the upper side. Meanwhile, a lower triangular matrix is like this, right? And basically what you're going to create is an upper triangular matrix. How? All of the other values that are not included in this triangle are going to be 0. So you're like, okay, how? Right? How are we going to do that? In this case, the upper triangular matrix is just this. So that means you're just going to have to make this 0. And sometimes, right, what you want to do is the edges of the triangle have to be 1, 1, 1. Honestly, it's up to you, right? You can just have them not at 1 for all I care, right? But I will turn them into 1s just so you understand how it's supposed to be done. And so now, excuse me, the question really does beg, the question really is, how do you get there? You're going to have to employ what we call elementary row operations. You're like, what is an elementary row operation? Basically, you're now changing the rows of this augmented matrix without breaking rules, established rules. Established rules in the sense of, well, in this case, you have row 1 and row 2. I will now be making a long list such that I will create, or I will log the changes that I will make. This is my first row operation. Very easily, we can just say that I will divide my row 1 in half and have that as my new row 1. So basically what I'm doing in here lang is that I'm just dividing everything in row 1 by 2. We can do that, right? We can add, subtract, multiply, divide. Everything there is possible. What do we mean? Let's just have this so far, right? 2 divided by 2 is 1. 3 divided by 2, -3 divided by 2 is -3 over 2. And then we will have here -10 divided by 2 is -5. And everything in the bottom remains unchanged. Next, what I will do now is I will remove this 5. How do we remove that 5? I will now log my change in here. I will now be changing R2. What I will do for R2 is now I will, right, R2 minus 5 times R1. R2 minus 5 times R1. Okay, why is it 5 times R1? Because now what we're doing is basically we are adding and subtracting rows. What you cannot do is something like this. Bawal yan, right? You cannot have everything subtracted by a certain amount. What you need to do is you can only create operations based on the rows. So in this case, this is legit. This is possible. In this case, because we are not coal. Because where are we? Here. Because nope, that's not it. Here. Because we are not changing our value for row 1, well, we can just have it unchanged. There you go. Now we will change our value for row 2. Row 2, 5, right? 5. In this case, minus 5 times what is the corresponding value for row 1? 5. 1. That will just be 0. You know what? Let's change, or let's highlight the values in red that we've changed. 1, negative 3 over 2, and then this is negative 5. Okay, let's continue. R2. So 1 minus 5 times 3 halves. Okay, let's have that. And we will basically have... Okay, we will basically have 1, right? So R2 minus 5 times R1. Oh, that's a negative, so this will become positive. Okay, so now we will have 1 plus, what is this? 15 over 2. So this is going to be 17 over 2. Oh, that 17 is coming up again and again. And now, what about this? Right, our 9. 9 minus 5 times R1. So that's a negative 5, so you'll make this plus 5. 25, 5 times 5 is 25, plus 9 is 34. Okay, now we basically have a row echelon form. But now I will make this, I will make this 1, right? So I will now divide everything in row 2 by 17 over 2. So I will multiply everything by 2 over 17. It does not matter that this is very complicated so long as it is, so long as it is a number. So in this case, right, we will have 1, negative 3 over 2. This is still 5. Negative 5. And now we will have 0 and then 1. And then if we multiply this by 2 over 17, cancel, you have a 2. 2 times 2 is 4. Where have we seen that value of 4 before? Now we are technically at our row echelon form. This is already our REF. But if you want to take things further, right, what we can do is we can put it into our reduced row echelon form. Right? Reduced row echelon form, let's just remove this 3 over 2. So how will we do that? Right? We will basically create our R1. How will we create our R1? We will create R1 plus 3 halves of R2. Right? We are using the fact that this is just a 1 to balance stuff out. This one will remain unchanged, 0, 1, and then 4. And notice that this will also remain unchanged because, well, your R1 is 1 plus 3 halves times 0. So nothing is going to happen there, right? And this one naman, right? This one is negative 3 halves plus, right? 3 halves times 1, which is this thing. Which the goal in here is to just turn it into 0. And then this one, right? Negative 5 plus 3 halves times 4. Cancel, you will have here 2. Negative 5 plus 3 times 2 is positive 6. Negative 5 plus 6 is 1. This is now your, what we call reduced row echelon form. And basically, from either of these two values, you can now get your value of x and y. Basically, let us now pull them apart. We have now gotten our matrix with these row operations. We can now get them to negative 1, 3 half, 0, 1, and then x and y. And then we get them to -5 and then 4. Notice that when you get them back into their simultaneous equations, you will get x minus 3/2 y is equal to -5. And then 1y is 4. So basically, you already have one answer in here. And you will just have to substitute your answer, cancel 2, right? And then that is now -6. You put that to the other side, that is now +6. Your x is now equal to 1. So, in this case, your row echelon form still has a little bit of algebra left, but it should give you the same answer, just like in Cramer's rule and the manual, quote-unquote, the manual way. The reduced row echelon form is even more direct in the sense that if you're going to bring this back, right, into your original matrix form, this is just our unit matrix, honestly. And now, because that is our unit matrix, you can just honestly cancel it. X equals 1, y equals 4. And notice, right? We have effectively gotten this simple answer from how many operations was that? 1, 2, 3, 4. 4 operations compared to creating Cramer's rule, creating the inverse of this matrix A. Okay? So that is the power of Gauss-Jordan elimination. Now, let's see this power, right? As we're heading on to 3x3 matrices. At this point, right, using the manual method becomes too unwieldy. Unwieldy in the sense that, there is a lot of freedom as to how we're going to get these functions to behave, right? The freedom is now, what can I do? What will I eliminate? What will I substitute? So on, so forth. It is all a little bit too much, right? In this case, though, let's try and use Cramer's rule. Cramer's rule is now basically creating the matrix form, right? Creating the matrix form. Hopefully, you guys know the pattern by now. 1, -3, 2, 3, 1, 1, -1, 2, and 3. This is now x, y, and z. This is going to be 9 to -11. And so again, we will have, right? We will have a x is equal to b. That means that your value of x, right? Your three variables in here is just gotten by using the inverse of a and then multiplying it with b. Okay, so let's try it out. By us, we mean I will now use my calculator, right? If A is going to be this matrix, this 3x3 matrix, of course, you guys can do this on your own, right? If you would like to see, if you would like to practice a little bit more into how to create the inverse of something, you're very welcome to do it here, right? -1, 2, 3. And so that means our inverse of A should be, right? Should be what? Let's try this out. -1, -3, 2, 3, 1, 1, -1, 2, 3. We will get what is the inverse of matrix A. The inverse apparently is, oh my gosh. Okay, 1/45. Uh-oh. And then 13/45. Oh boy. Right? -1/9, which makes me think that the determinant is 45, and this is just -5/45. Next, we will have -2/9. Next, we will have 1/9. Next, we will have 1/9 here as well. +7/45. We will have 1/45. And then we will have 2/9 here as well. Okay, so that is our inverse. So apparently our determinant is 45. I can kind of see how it's 45, but well, I don't have the patience to do that, right? But again, the process should be internalized, right? And then let's try and put that to the test and multiply it by b. So we will have basically in here 1 over 45. I will pull out the 45 everywhere. This will just be 1, 13, negative 5, negative 10. What is this? 5, 5, 7, 1, and 10. Then we will multiply it with b, which is 9 to negative 11, which is, that is a lot to take in. 1 over 45. Let's just try this out. Okay, we will have first row only column, first row only column. 9 plus 26 plus 55. Oh, that's already a lot, right? 35 plus 55, that is 90. Oh, 90. Okay, looking good. Next, second row only column. Negative 10 times 9 is negative 90. 5 times 2 is 10. 5 times negative 11 is negative 55. So we will have in here negative 135. Okay, negative 135. Hopefully that also rings a bell for you guys. Right? And then finally, our last bit. Right? Last row only column. 9 times 7, 63. 1 plus 2, 1 times 2 is 2. And then 10 times negative 11 is minus 110. So that will be equal to negative 55. Oh, sorry, negative 45. And now, finally, we get to our answer in here, right? That means that your value of x, which is your x, y, and z, is just equal to, right, 2, negative 3, and negative 1. Those are our answers, right? Those are our 3 answers. And that's using Kramer's rule. And technically, what I'm doing here is I'm not using Kramer's rule. I'm creating in here the inverse and then so on, so forth. Kramer's rule is a little bit different. What it's doing in here is basically it's telling you, hey, if you can get the determinants of things, you can get the answers pretty easily. Say, for example, letter x tuloy. X in here, the value of x will be just the determinants between two things. What do you mean two things? First, the denominator, the determinant in here will be, the denominator will be the determinant of your original matrix. You will have here 1, negative 3, then 2, and then 3, and then 1, and then 1, and then negative 1, and then 2, and then 3. Now notice that x is the first row. That means you will now replace the first column, first row, first column. You'll now replace it with the answer, the quote-unquote answer, as in this thing, 9 to negative 11, and then everything else remains the same. Now, if you get the determinants for those of both of these things, you should get 2. Sorry, code. And then, sorry. And then you will repeat for y and for z. For y naman, okay, she's gone back to sleep again. For y naman, you will have two giant determinants again. And let me just copy paste this thing. There you go. Copy paste. Have this here. And then you will copy paste this determinant here as well. And here. But now I will replace the middle one because the second column, right? You will now replace that with your answer, quote-unquote answer, 9 to negative 11. And then so on, so forth. And honestly, I can just copy paste this whole thing. Replace this with z. Oops. Replace this with z. And now this thing 3, 1, 2. This gets replaced with, this gets replaced with 9 to negative 11. So if you want to do that, go ahead. But as you can see, Kramer's rule is only good if you can get the determinants. What about 4 by 4 matrices, right? That is where Kramer's rule starts to fail. And, well, you can now back generalize to here, right? Your immediate value for x will just be based on the determinant of this thing, 2, negative 3, 5, and 1. And the first, right, because this is the first variable, right, you will replace the first column, right, you will replace the first column with the answer, negative 10 and then 9. So go ahead, right, if you want to do so, do it now, right? This thing, we know the determinant of A of this original matrix is 17, so I already know that. Now 10 times negative 10 times 1 is negative 10. 9 times negative 3, negative 27. Negative 10 minus negative 27 is, surprise, surprise, 17. This is going to be 1, just like what we know from earlier. Where is that thing? This thing, right? There you go. Okay, now, right? This depends on if you can get determinants easily, which is still somewhat, right, related to getting the inverse. So if you do not want to get the inverse, you can just do Gauss-Jordan elimination. Okay? Gauss-Jordan elimination. Let's create here our augmented matrix. 1, 1, negative 3, 2, 3, 1, 1, negative 1, 2, 3. In our augmented matrix, honestly, I could not be bothered with the broken line. So we'll just do 9, 2, and then negative 11. So after this, we can go, right? This is now our this is now our augmented matrix. What I will do is that I will do this now in 2 stacks. This one we've done in 4, right? In 4 operations, row operations. So this one hopefully will do it in not a lot of operations. As small as possible will do it, right? And so now what we will do is get this to its row echelon form. This. So as you can see, okay, this is already at 1. So no need to change this, but although we will see later it will be changed. So don't get your hopes up, right? What we will do is first, right, get this to be 0, right? Okay, let's try that out, right? Let's try that out. And what we will do is create row 2 and then minus 3 times row 1. That will now be our value of row 2. Okay, so hopefully we understand what's going on. And yes, there you go. Copy, paste. There it is. I love technology. We will now replace all of this and we will turn this red. 3, right? Minus 3 times 1 is, of course, 0. Next, 1 minus 3 times negative 3 is this, which makes this 10. Okay, interesting. And then, next, right? 1 minus 3 times 2, this is now 1 minus 6, which is negative 5. Next, 2 minus 3 times 9, this is now going to be negative 27. 2 minus 27 is negative 25. Okay, I can see in here, right, that everything in here has a factor of 5. So honestly, you can do a little bit of transformation already. If you spot that, go ahead, divide everything by 5, right? So I will now divide everything by 5. Actually, let's just try and copy paste. Oops. Let's try and copy paste everything in here. Copy paste. I love technology. There you go. We will now divide R2 by 5. We will get, right, 10 divided by 5 is 2. Negative 5 divided by 5 is 1. Negative 25 divided by 5 is negative 5. Now, our next goal is to turn this into 0. We are creating slowly but surely our upper echelon form. Our row echelon form. So this one is 0. Now our goal is to just, transform this, right? The third row now into 0, right? The third row first column, right? And so therefore what we should change in here is R3. Okay, what should we change it into? Well, R3 can just be added to R1. We have here -1 and 1. Apologies for the notifications, right? We will now have, well, this one will be all white. How do we turn that white? Okay, there you go. Everything will now be white. And then, oh, sorry, row 3. We're changing row 3. Right? And as you can see, right, nothing has changed with row 1. So we can just refer to this thing and then this thing. Right? -1 plus 1 is 0. Okay. Next. What is this? 2 minus 3. Right? 2 minus 3 is -1. Okay. And then 3 plus 2 is 5. Okay. And -11 plus 9 is -2. Okay. Now what? What we will now do is make this into 0. Right? So we are creating that row echelon form. And again, we do this, copy, paste, and then we go here. Of course, this would go easier with your digital device if you have a tablet or something like that, right? Of course, it also works on paper. It's just that you can't copy paste on paper, right? We will again, right, play around with our row 3. And now, how will we play around with our row 3? Notice that our row 3 is currently at -1. So, maybe what I want to do in here first is to multiply row 3 by 2 and then add it to row 2. Why? Because now, -1 times 2 is -2 plus 2. That's now going to be 0. Okay, next. 5 times 2 is 10 minus 1, because this is 1, that will be 9. Okay. And then -2 times 2 is -4. Minus 5 is, oh, surprise, surprise, -9. Now, everything is almost set. The last bit, because we see that there's a common factor of 9, might as well take the chance, right? We divide everything by 9. R3 divided by 9 is your new R3, which means this is going to be 1 and -1. We are already at our row echelon form. And honestly, at this point, you can just back solve for everything. As you can see, z is equal to -1 because of this equation right here. Good, right? And then now we see that on the second equation, we will have 2y minus z is equal to -5. So we can just substitute our value of -1, 2y plus 1 is equal to -5. Lipat sa kabila, we will have 2y is equal to -6, which means our y value is -3. And then finally, we have our first equation, which is x minus 3y plus 2z is equal to 9. So let us multiply or substitute our values. -3, -3. 2 times -1 is equal to 9. We will have x plus 9, right, minus 2 is equal to 9. So cancel, lipat sa kabila. We will have x equals 2, which does agree with our 2, -3, and 1, right, as our row vector from before. But of course, this one has the help of a calculator. Thank you to my Canon, right? But in this case, this is all mental, this is all mental, right? As you can see, right, Gauss-Jordan elimination is very useful, especially if you do not have a calculator or if you are not allowed to use your calculator, or if you are doubting your calculator, which, why would you, right? If you want, you can, of course, reduce everything in here to reduce row echelon form, but I'll leave you guys to that. Okay? I'll leave you guys to that, right? So that is it. That is our first application for linear algebra. It is solving simultaneous linear equations. And for next time, we will be solving simultaneous linear differential equations. So that's very exciting. We are now connecting, right, our topic 1 and our topic 2. So I will see you for the next one. Thank you.